Hello everyone. These are our notes on exponential functions, which is the last section in this chapter 1 grouping of topics. And this chapter was just all about different functions. We talked absolute value, piecewise, inverse functions. Lastly, we're talking about exponential functions, which will tie in all of those properties of exponents that we've been learning about, and properties of radicals and rational exponents. That was getting some base knowledge so that we're ready to talk about exponential functions and we're ready to understand what these are and how they're used to model tons of different situations. So we're going to talk about graphing and we're going to model lots of different situations using exponential growth. So you might have heard this before, saying something grows exponentially. Or for example, if you've ever talked about in science class, cells cutting in half and growing that way. Or when talking about bacteria or viruses, for example, we're seeing this in the news with COVID having exponential growth. We're going to talk about this here. So our learning objectives are, I can define an exponential function. I know how to write it. I know what it is. And we can graph exponential growth and decay functions. So sometimes we have exponential growth, and then sometimes we have exponential decay. What do those look like? And now I can write exponential formulas to model exponential growth or decay. And lastly, I can write recursive rules for exponential growth. And this recursive rule will be new for you. This is going to be something brand new. So we'll work through that together. And those are our goals for this lesson. All right, so exponential functions. This is a nonlinear function in the form y equals a times b to the x. You see this x is in the exponent? That's important. This indicates exponential growth. And you see my graph here, we have a times b to the t, and that's because exponential growth is often modeled with time along the x-axis. So that's why sometimes you'll see a t here instead of an x. But just know that t and x mean the same thing. So for this, t equals x. All right, so what does it mean for something to grow exponentially? This means that, for example, let's say time equals 0 or x equals 0, y is also 0. So we're starting at 0, 0. Let's say after a year, we're going to be at 1. Or excuse me. Let's say we're starting at 1. Let's say at time 0, we're starting with 1 item. Then after 1 year, we double it. After 2 years, we're going to double that. So this will be double 2, which is 4. After year 3, we're going to double that amount. So double 4 is 8. After year 4, we're going to double 8, which will be 16. After year 5, we're going to double 16, which will be 32. You see how we're growing faster and faster the more we go on. That's exponential growth. Or if you're looking for a chart, you know how linear we would have a factor that's the same? For exponential, we're looking to multiply by a certain number from y value to y value. So from each of these y values, we multiply by 2. So when you multiply by a number to get to each y value, that's exponential growth. Because remember, an exponent is just multiplying by a certain number over and over again, as many times as indicated. So this is going to be times 2 as well. Okay. And now this factor right here, this 2, this growth factor, is our b right here. So this b is the growth factor. I'm going to say growth / decay factor, because it depends if it's exponential growth or exponential decay. If it's decay, then b is between 0 and 1. So it's a fraction between 0 and 1. But if b is larger than 1, then we got exponential growth, and we are growing exponentially. And then this a value right here will be whatever your initial amount is. So when x is 0, what is y? And if you were to graph this class, exponential functions start out slow and then rise faster and faster and faster. So they rise very fast after a period of time. It's exponential growth. We grow exponentially. All right, and there are two different formulas to represent exponential growth or decay. This one is just talking about this growth factor b times your initial amount and raising this factor to the power of t or x. This one is dealing with rates. So a will be your initial amount times 1 plus your rate, so like 20% would be 0.2 to the power of t. This will be used to model like population problems. So for example, if a city has 30 million people and it grows at a rate of 2% per year, what will the population be after 4 years? We often see population modeled as exponential. So the population of our planet, of all the people here, is growing exponentially as of right now. Obviously, there will be a limit. We can't have, 200 billion people living here. Maybe. Okay. So this is the form of an exponential function. There are two different forms, two different ways to describe, but keep in mind this t or this x value is always an exponent. That is key. That's the key here. All right, now let's talk about some vocab that we need to know to be able to go through here. This word, asymptote. An asymptote is a line that a graph approaches more and more closely. For example, this blue line here, see this line, if we go to the left, this will approach the this x-axis, it'll get closer and closer and closer to it. That means that the x-axis is an asymptote for this graph, because the graph will get closer and closer and closer to it. Now, recursive rule is a rule that gives the initial value of a function, f of 0, and then some recursive pattern. And recursive just means that it's how the next term in the sequence is related to the preceding value. So it's just a way to define the function that to help you find the next term in the sequence given the previous term. That's what this means. And you just heard me say the word sequence. And a sequence is just an ordered list of numbers, a set of numbers that follows some sort of pattern. Because class, remember that mathematics is just the study of patterns. So these two are very strong in our mathematical reasoning here. So here are two sequences, 5, 10, 15, 20. The pattern is add 5. Here's a sequence, 2, 4, 8, 16, This list can go on forever. This one multiplies by 2 to get each term. So we're going to talk about how we can represent exponential functions as recursive. So we'll write a rule to represent them. And we got parent functions. So remember that a parent function is the function in its simplest form. And this is a graph for exponential growth. And this over here is a graph for exponential decay. So for growth, you see we start out slow and then rapidly grow faster. For decay, we rapidly decay and then we slow down as we get closer to 0. One way to think about exponential decay is if you're standing somewhere and you're looking across the room, exponential decay would mean something like, okay, you're going to walk from where you are halfway across the room. So you'll get halfway across the room. And then you're going to walk from that midpoint halfway again. And then halfway again, and then halfway again. You'll get closer and closer to the wall, but you will never ever touch the wall. You'll just be getting infinitely closer forever and ever. Okay, so some key parts. Both of these intersect the y-axis at 1, at y equals 1. And they both have asymptotes. The x-axis is an asymptote for both of these. So both of these will approach the x-axis, but they won't actually cross it. And these are our parent functions. All right, let's talk about graphing exponential growth and decay. So first, we'll tell whether each function represents growth or decay, exponential growth or decay, and then we're going to graph it. Okay, so this first one, A, 3 times 2 to the x. This 2 is larger than 1, so this is exponential growth. Exponential growth. And I think to graph it, I think it would be helpful to create a table of values. So I'm going to start with 0, and this is going to be an XY table. X, this is a Y. Come on, friend. All right, XY. 0, 1, 2, 3, 4. Let's go to 4. So 0, when x is 0, y is 3 times 2 to the 0 power. And this is where our properties of exponents are going to come in handy. Because class 2 to the 0 is 1. So we really have 3 times 1, which is 3. So when x is 0, y is 3. Now if x is 1, then we have 3 times 2 to the first power, which is just 2. So we have 3 times 2, which is 6. Now if x is 2, we have 3 times 2 to the second power, which is 3 times 2 squared, which is 4. So we have 3 times 4, which is 12. Now if x is 3, then this is 3 times 3 squared, which equals 3 squared is 9. 3 times 9. Excuse me, this should be cubed. 3 cubed. There we go. Excuse me, I made a mistake, didn't I? This should not be a 3 in this. We're taking 3 times 2 to the power of x. So this should be 3 times 2 to the power of 3. There we go. So 2 cubed is 8, and 3 times 8 is 24. You might be noticing a pattern with all these y values. See, 3 to 6, we multiply by 2. From 6 to 12, we multiply by 2. From 12 to 24, we multiply by 2. How about to get to this one? We're going to multiply by 2 as well. It's a pattern. So this one will be 24 times 2, which is 48. Okay, let's graph this. So I'm going to say this is 0, just for the sake of my computer being small. I'm going to say that's 1. This point is going to be 2. This point will be 3, and then we'll be off the graph at that point. So at x equals 0, y is 3. We put that in, that's in our table. So I'll put that point here. When x is 1, y is 6. That's right here. When x is 2, y is 12, which will be up here. We're just going to keep going higher and higher at a faster rate. Now let's go back. Let's do when x is -1. So we get at least one more point here. -1. Okay, so 3 times 2 to the -1 power. Remember that this negative exponent means we divide by 2. So this is really 3 divided by 2 to the first power, which is just 3/2. So that means 3/2 is 1.5. So this will be a point about right there. And then we just get closer and closer to the x-axis going forward. So this represents exponential growth because this b value right here is larger than 1. And then we create a table of points to plot this. All right, now let's try part B. So this is 2 times 1/3 to the x power. This 1/3 is between 0 and 1. So this is exponential decay, which means we're going to look something like that. But we'll find some exact points here. So again, let's create an x and y table. And let's pick some values for x and y. I'm going to, again, start with -1, and then we'll go 0, 1, 2, 3. So when x is -1, y is 2 times 1/3 to the -1. Now 1/3 to the -1 power, that means we divide by 1/3, which is the same thing as multiplying by 3. This is really 2 times 3, which is 6. So we can plot this point at -1. This function value is 6. That's one of our points. How about when x is 0? This is 2 times 1/3 to the 0 power, which is anything to the 0 power is 1, so this is just 2. So when x is 1, our function value is at 2. Oh, excuse me. Nope, when x is 0, we're at 2. All right, how about when x is 1? So we just have 2 times 1/3 to the first power. This is 2 times 1/3, which is 2/3. We're already getting small. We might just be done after this one. This one will look like this. So we get closer and closer and closer to that x-axis. That's not steep enough. And this is an approximation of what this graph will look like. So as long as you understand how to create a table of values, and this is why we worked so hard on our properties of exponents, so we can understand negative exponents, so we can understand 0 exponents. This is why. So now we can model information using exponential functions, which use properties of exponents. And one other thing to know is exponential decay. Remember, we decrease faster, faster, and then slower, 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 and we kind of level out here. And that's how we graph exponential growth and exponential decay equations. All right, here's our objective 3, writing an exponential model. So, at the start of 2016, the population of Des Moines was about 216,000 people. The population at the beginning of each subsequent year increased by about 1%. So that means each year after, the population increased by 1%. We're going to write an exponential growth model that represents the population y in thousands t years after 2016. So, do you remember at the beginning of the notes, we talked about 2 different forms to represent exponential functions. One of them is y equals some number a, times b to the x power. There's another one. Y equals a, so your initial amount, times 1 plus your rate to the power of x, or to the power of t. This one is most often used with time. This one is most often used to whenever you're talking about exponential growth in the term of a percent of an increase. That's what this r is. This r is your rate. So hey, we have a rate here, so we're going to use this function here. So we're going to use y equals some number a times 1 plus our rate to the power of, I do say t years, so this will be to the power of t. Okay. Now, first, figure out, is this exponential growth or decay? Is our population increasing or decreasing in Des Moines? We increase, so this is exponential growth. All right, now, we need to figure out what this a value is and what this r is, and then what our y and t mean. All right, so if we're writing an equation to model the population y, that means y is the population in thousands. t years, so t represents years after 2016. So let's actually talk about that. T equals 0 is 2016. And A, let's talk about A. This value A equals the initial population, the initial amount. The initial population, because this A value is the y-intercept, or the value, the population at time equals 0. This is the population at t equals 0. And our rate, so this 1% is our rate. So R for us is 1%. We're going to use this in decimal form. So 1% as a decimal equals 0.01. Remember, we just divide by 100 to get from percent to decimal. All right, class, we know A, we know R. That's all we need to know. So our initial population is 216. So this is our A value up here. Now, our equation is y equals our population equals our initial population when time is 0, which is 216,000. But remember, our population is in thousands, so I can just write 216, and I know that that number represents 216,000. 1 plus our rate, which is 0.01 to the power of t. So we can simplify this. This is y equals 216 times 1.01 to the power of t. And this is our population equation right here. Now, we're going to find and interpret the y value when time is 5.5. I'm going to do this two ways. We're going to do this using our formula, and we're going to figure this out using a graph as well, because I want to graph this. So, find and interpret the y value when time is 5.5. So, our y value we're looking for. But we know that y equals 216 times 1.01 to the t, but hey, we're saying t is 5.5, which means after 5.5 years, we're going to find y, which is the population. So now, using our calculators, we're going to find 1.01 to the 5.5 power, and then we're going to multiply that by 216. And we get 228.15 about. Which this means this means 5.5 years after 2016, aka 5.5 years after 2016, so 2021 in June. The population will be 228.15 thousand people. So class, all we did was plug in 5.5 for t, knowing that when t is 0, that's 2016. So this is 5.5 years after 2016, which will be 2021 in June, because a half year will bring us from January to June. And then this 228.15 was our population in thousands. So in 2021 June, the population will be 228.15 thousand people. Now I mentioned wanting to graph this and figure this out graphically. So if you follow me to this screen, I graphed our exponential function. And first things first, does this look like exponential growth? Yes, we start slow, we rapidly get faster and faster. Now my range is very large. So this is where we're starting, and when time is 0 at 2016, our population is 216,000 people. That's good. So this y value is the number of people in thousands, and this x value is the number of years. So we're looking for when x, in class I wrote x instead of t because Desmos doesn't like it when you write t. They think you're creating a slider. Oh, never mind. Oh, okay. Scratch that. I can use t. So we're looking for when t is 5.5, right, class? What? T equals 5.5. Oh, interesting. Okay. Desmos is finding this for us. Desmos automatically typed in 5.5 for t and got this value. Alright, so Desmos will calculate it for us. I would like to go back and use x's here and use x here. Okay, so now you see we have two different lines. And I'm going to change our x-axis to go only until 10. From -10 to 10. Okay. So this red line, remember, is our exponential function. This blue line is just to show when x is 5.5. So if we find these intersections, we find when the time is 5.5, which is the x value, and our y value will be the population, so 228.15. So you could have just found this answer by using the graph only. So as long as you know how to do it both ways, you're in good shape. So remember, we're just looking for our exponential graph and then where that graph crosses this line, x equals 5.5. And that'll tell us the population at that point. So we could figure out the population after 10 years. Let's go to 10. Whoops. When x is 10, the population will be about 238.6 thousand people. All right, we'll go back to the notes. Let's estimate when the population was 220,000. Let's use the graph for this. So 220,000. We passed it here. What about when x is 9? Our population was 236,000. What about when x was 5? Population was 227,000. So it's going to be less than 5. We need to go down more. How about when x is 3? That's 222,000. That's pretty close. What about when x is 2? That's about 220,000. So we can estimate this by saying around year 2, the population was 220,000. All right. Estimate when the population was 220,000. So I'm going to say graph on Desmos. We graphed our equation y equals 216 times 1.01 to the x, or to the t. And we found when x equals 2. So in 2018, because that's what it means when x is 2. It's 2 years after 2016. In 2018, the population was about 220,000. Desmos is a very helpful tool when discussing modeling exponential growth. There are a lot of different things that graph can tell us. So it'd be very useful for you to know how to use Desmos, know how to interpret the graph. It's really important in most jobs that you'll end up with too. It's important to understand how to graph things and what it actually means. All right, here's our objective 4. Writing recursive rules, which is where the next term depends on the previous terms. I have some exponential growth ones. Like this one is exponential growth and B is okay, most of these are exponential growth. And then I have a challenge one that's not exponential growth, but it's always a fun one. All right. And then we've got 2 more example problems to determine if we're representing exponential growth or decay. So this is using our flexibility of exponents. And then we've got one last application problem, and then that's it for these notes. So let's go back up here. And let's talk about writing recursive rules. All right, y'all. So the key here is that you're going to write a rule that shows where to go for the next term based on what the previous term was. And there's a formula that we can use for this. So I'll write that up here. So we can write, here's our formula. I'll just write this here as a big side note. After I actually scroll down just a tiny bit. So we can do 3 examples. All right. So our rule, since this is brand new, I'm going to talk about it. So we're going to start with whatever our first term is. So f of 0 equals, it's going to equal some number. So for example, our first term here is 1. For this term here, it's 3. For our first term here, we'll talk about it, but it's going to be 4, and this one will be 9. Okay. Now, we can write a formula to find our nth term. So f of n is going to equal our growth rate, or our growth factor, or our decay factor, times our previous term, which is f to the n minus 1. And class, this will make sense if we can see some examples. There's a lot of letters, but let's talk about some examples. So we literally write this as our rule right here. That's what we'll write. So for example, this first one, a, will be f of 0 equals 1, because that's our first term. Now, to get from each term, or to get to each term, we're modeling exponential growth, so we multiply by 3 to get to each term. Do you see that? We times 3, times 3, times 3. So we multiply by 3 to get to each of these terms. So our growth factor, our b factor, is 3. So class, all this means is we're going to write f of n, or x, equals our growth factor times our previous term, which is just f of n minus 1. That's just what this means. This means from f of n, to find f of n, we're going to take 3 times the previous term. So for example, to find 81, which is f of 0, 1, 2, 3, 4, f of 4, we're going to take 3 times the previous term, which is 27. To find 27, which is f of 3, we're going to take 3 times the previous term, which is the second, or term like 0, 1, 2, f of 2. You see where we're going here? Now, this guy, we start at 3, so f of 0 is going to equal 3. And you see how we're multiplying by 2 to get to each of these? So our growth factor, because we're growing, so our growth factor, b, is equal to 2. So this means we can write f of n equals 2 times the previous term, which we call f of n minus 1. All right. Part C. We're not given a sequence anymore. Oh, I didn't tell you. These are sequences, yeah? Patterns, pattern of numbers. Now C, we're just given a function. And we need to figure out what f of 0 is. So we plug in 0 for x, and we get 4 times 7 to the 0, which costs, that's just 4. Because remember, in our exponential functions, this number out here is our starting point when x is 0. So this is our first term in the sequence. And now, any term in the sequence, I'll use f of x since our function was written as f of x. We can write f of x equals our growth factor, which will be 7, times the previous term. So So 7 times f of x minus 1. That's how we would find the next term in this exponential growth sequence. by taking 7 times the previous term, because each term will grow by a factor of 7. That's the definition of exponential growth. So now let's take a look at part D, and I'm going to leave E as a challenge. I'll leave that up to you. So if you feel the need to challenge yourself with it, try it out, and then visit me if you would like me to check it out. But this is a very, very special sequence in math. It shows up everywhere in nature. It's very, very cool. But for the sake of this video, it's getting very long, and I know that. I'm just going to skip it. So D, y equals 9 times 1/3 t. This 1/3, class, means exponential decay. So f of 0 equals 9. That's our initial value right here. Now f of n equals our decay rate, which is 1/3, times f to the n minus 1. That's how we would get to the next term in this sequence. I know this is difficult, so if you still have questions on this, email me or hop on my office hours or just come talk to me during win time. Come see me if you need any help with this writing recursive rules given a sequence or a function or an equation. Because now we're moving on. All right, now we're going to rewrite each function to determine whether it represents exponential growth or exponential decay. And then we're going to identify the percent rate of change. All right, y'all. First, we need to talk about this percent change word. So everything here is going to be based off of 100%. For example, if yesterday I gave 110% of my energy to teaching, today I gave 107%. What was my percent of change? So what's the difference there? How far away is 107% from my 100%? That's 7%. So I would say my percent rate of change was 7%. What if I wasn't really feeling it? I only gave 92%. What was my percent rate of change? What's the difference between 100 and 92? That's 8%. So I had an 8% decrease in my general energy level. So that's what that means when we say general percent rate of changes we're based off 100%. So our difference between 100%. Now, with these, we know if something represents exponential growth or decay if it's written in the form y equals a times our b to the t. Y equals a times b to the t. Because if this b is larger than 1, then it's growth. But if it's between 0 and 1, then it's exponential decay. But with these examples, you see this example right here, which f of t, which is like y, equals 3 times 1.02 to the 10t power. See, normally we just have it to the t power, but we have this 10 here now. So I want to try to use our rules of exponents and our flexibility with these numbers to be able to write this as something just to the power of t so that we know if this is exponential growth or decay. Now, as a side note, you don't have to write this down if you're taking notes, but let's see, x squared to the 3rd power, we can simplify this, right? We can multiply these exponents, and this is x to the 6th power, x to the 2 times 3. Well, y'all, can't we write 1.02 to the 10t as 1.02 times 10 to the t power? Isn't that still the same thing? And then we will have a number once we evaluate 1.02 to the 10th power, and then we'll have a number to the t. So I'm going to go ahead and write that here. This is 3 times 1.02 to the 10th power to the t. Now I'm going to use my calculator to find 1.02 to the 10th power, which is 1.219, I'll round it to the t. And now this helps us determine exponential growth or decay, because this is larger than 1, So we have exponential growth. Exponential growth. And if you were to graph this, you can see that it would curve like this. Now this one, we have y equals 0.95 to the t plus 2. This whole thing is in the exponent. So how do we navigate that? This is again using our rules of exponents. So we can say, what example should I do? Let's do 3 to the 6th power times 3 to the 4th power. Because if we have two things with the same base and different exponents, we can add those exponents, can't we? 6 plus 4, which would be 3 to the 10th power. Well, you see here, we just have the opposite of that. We already have an addition in our exponents. So couldn't we just say this is really y equals 0.95 to the t times 0.95 squared? Because now these have the same base. If we wanted to go back here, we would have to add these exponents. And now we can use our calculator to evaluate 0.95 squared. And y'all, I'm also going to just go ahead and bring this to the other side and evaluate it. So this is 0.9025 times 0.95 to the power of t. And now this is in our form that we like. Y equals some number a times b to the t. And since this is less than 1, or between 0 and 1, so we have exponential decay. All right, so you see this just takes some flexibility with our exponent rules to be able to manipulate these formulas to get them to look the way that it is familiar to us so that we can identify growth or decay. And remember that decay will look like this if you were to graph this. All right. Excuse me, because I forgot to find the percent rate of change for both of these. So let's first find it for this example to the right, since we're just working on that. Percent rate of change. So, percent growth, we're going to be looking at this. And now, 0.95 as a percent is 95%, right, class? And now remember, percent growth is based off of 100%. So this is really not growth at all. Our percent of change, is based off of 100%. So this 95% is not growth, it's a decrease. And this is a 5% decrease because we're 5% away from 100%. So it's a 5% decrease. Now this guy, this decimal is 1.219, which is, as a percent, 121.9%, which means we had a 21.9% growth, or a growth of 21.9%. All right, now these problems are complete. Email me if you have any questions about them, all right? Now let's go down and let's do our last problem in this video. This video is long, so thank you for sticking with it if you have. So now let's talk about depreciation. So the value of a car is $15,000. And y'all, as time goes on, you know that cars lose their value. So this particular car loses 10% of its value every single year, which is called depreciation. Everybody's car depreciates every year. It's worth less and less every single year. All right, y'all. Step 1, we're going to write a function that represents the value y in dollars of the car after t years. All right, y'all. Now, if you go back to the beginning of the notes, you see that our two functions for represented exponential growth or decay. On the right-hand side, you'll see y equals the initial value a times 1 plus a rate to the power of t. Or we can write this as y equals a times 1 minus the rate to the t. And this guy, the second one, the bottom one, is used for decay, and this top one is used for growth. So I need you to determine if we are using exponential growth or decay each year. Y'all, we're losing 10%, which means our value is decaying exponentially. So we're going to use this formula right here. So I'm just going to go ahead and write that in this box to give us a starting point. Okay, so we got y equals a times 1 minus r to the t, where r is your rate. So this means our rate is 10%, which as a decimal is 0.1. This is our initial value a, because that's when time is 0. That's the value of the car. And then y will be the value of the car, and t will be the time in years. So now we just need to plug these into our equation. So we end up with y equals 15,000 times 1 minus 0.1 to the t, which we can write as 15,000. 1 minus 0.1 is 0.9 to the t. This is an equation that we can use to model the situation. Now, let's find the approximate monthly percent decrease in value. So how much does this decrease every single month? How much does the price decrease every single month? Well, to do that, let's look at this guy right here. So this is 0.9, which is 90%. So what's our percent of change? Well, we lose 10% every year. So per month, we'll take 10% divided by 12 months. In class, 10 divided by 12 will be about 0. I guess I should write it. Per month, 10/12%, or about 0.83%. So you lose about 0.83% value every single month that you have this car. All right, in this last box, we're going to graph this function, and then we're going to use that graph to estimate the value of the car after 6 years. So I'm going to go over to Desmos. I'm going to get rid of these old functions. I'm going to write 15,000 times 0.9 to the t power. Okay, I'll add x this time. Y equals this. And we need to go all the way to 15,000, so we need to go way up high. All right, y'all. 0, 15,000. Good. That's our starting amount. That's good. I'm actually going to decrease my x-axis just a little bit to make it a little bit easier to see us. Let's go to 50, and let's go this to negative 50. All right. This is a little bit more reasonable to see. I forgot. We are estimating the value of the car after 6 years. So this is when x equals 6. Well, about the value of that car be? $7,971. So 7,971. It'll be about $7,971. So after 6 years, our car's value is about cut in half. And that's all I have for exponential functions for you. This was a long video, so thank you for watching. And email me or come in and see me if you have any questions at all right? Have a good day.